So we are alive. So welcome everybody. It's been a long time. Hello. Yeah, I see Diego again, Bob, Barry, all the usual suspect from the community. So good to see you, everyone. Welcome to this Q&A session. Maybe we should wait 2 or 3 minutes to see if more people join before we start. Yeah. So I will start the presentation. I have some slides to share with you about community and a few other stuff, and then I will hand over to our friend Carlos here, the main lecturer for the this upcoming course on quantum hardware, to talk to you, to share a little bit about the course structure and these type of things. So. Yeah, I think there are more people joining. This is good. Yeah, Diego, you're welcome, Diego. Good to see you again. Diego is saying thank you for organizing this. Yeah, as you can see, we are moving away from just providing abstract mathematical stuff. We are moving more into applied stuff, which the abstracts also have application into these things nowadays. In fact, it's nowadays the boundaries between pure maths and applied is becoming a little bit more complicated. Yeah. Yeah, we have more people joining. Excellent. Yeah. Hello, George. Hello, Safayette. I hope I'm pronouncing your name correctly. Yeah, so maybe we should start because I have some the course content, the stuff with the Carlos will be in about 10-15 minutes after my side. So. And this will be recorded anyway. I mean, it's being recorded right now, so people can rewatch again. So let me just pull up my slides. Okay, well, thank you. Let's see. I've lost practice with the crowdcast. Yeah, it's a screen share. Okay, so can everyone see the slides? They are loading. So most of you already seen this, so it's just a quick intro about what quantum formalism is. So for those of you joining us, quantum formalism is a free online course organization, that provides a series of courses, by Zaiku group. The idea is to expose advanced, or let's say abstract mathematical structure. Topics related to nascent industries, like emerging industries, like quantum computing. In the case of quantum computing, we are in two type of audience in particular that we try to target. This is not to say that if you don't fit in these two categories, you are not welcome. But we are particularly keen in people from diverse technical background. Say, for example, maybe the people are coming from software engineering background or other STEM subjects, and they want to get into quantum computation as professionals. But obviously, because quantum computing is a new paradigm of computation, there is some learning curve, especially on the mathematical side, where people need to learn, depending on how sophisticated people need to be, pretty sophisticated mathematics that normal people like engineering stuff don't get exposed to, things like Lie groups, representation theory, all these type of things that are very important, especially for those who want to get into quantum algorithms, but also quantum hardware as well. So you cannot run away from mathematics. In quantum computing now, very often I hear people say, "Oh, you only need linear algebra or whatever. You don't need well, maybe to get the introduction stuff, but introductory basic stuff. But if you want to go to the next level, you cannot run away from the mathematics. because the abstraction haven't been built yet. You can't just write a Python thing, and don't understand what's going on under, say for example at gate level, for instance. So it's very important, yeah. And you will see also the same thing with the hardware as well. I will give some reasons to why, in our case, we are very keen into having this quantum hardware course. Okay, so that's the first set of professionals, people from, coming from other industries, from other technical background. They want to jump into quantum computing, but they need maths, the abstract maths, a little bit more advanced than what they got into their engineering during their engineering degrees. The other set of target for us is actually the existing professionals, maybe people who are already in the quantum computing industry, but they want to revise certain topics, or maybe they were not exposed to certain topics in a more mathematical fashion, in a more rigorous fashion, because very often in engineering degrees, people are focused more on computational aspect of things, know how to compute something rather than proving. Yeah, and in quantum computation, you need very often, if you are building something, you need to prove. You need to feel comfortable making proofs. Yeah, so people coming from engineering background normally are give so much emphasis on computational, knowing how to compute stuff, as opposed to knowing how to prove things. Yeah, so this is one of the things that so these type of people are actually the people that we aim at, but this is not we're not saying that everyone else is not welcome, and anyone else is obviously welcome, because this is an emerging industry. We need as many people as possible. But yeah, just a quick overview about quantum formalism and who the ideal target audience for us is. And then our courses, because this is like most of the topics that we cover is a little bit advanced. Yeah. However, it helps really the ideal prerequisite for people before taking any of our courses, including, you will see Carlos's course on quantum hardware, is to have some basic university level exposure to mathematics, say undergrad, maybe advanced undergrad, like third year or something. Because if you have that, whether you are coming from engineering or physics or other STEM background, you would have probably learned a bit of calculus, real analysis, very often actually in a lot of undergrad programs, calculus and analysis are bundled all together into one. Yeah, linear algebra, yeah. Not necessarily the abstract linear algebra, the mathematician's fashion, but the computational linear algebra, knowing about how to compute matrices and this type of stuff. And in the Carlos's case as well, differential equations, that also knowing a baseline knowledge of that, this would also be helpful. So, but any of these, like, if you have this, it will be very, I wouldn't say very easy, but it will be easier for you to observe the abstractions that our, courses normally require. The maturity, the mathematical maturity level that our courses will require. If you don't have this, it's okay, but all it means that it will be harder for you. The learning curve will be steeper, but it doesn't mean that you should give up. But yeah, it's definitely very helpful if these topics. This is automatic if you are coming from you have university level exposure to mathematics, whether through engineering or other STEM topics, because you would have come across these topics. Okay. Let's see. There are more people joining. This is great. Another thing I want to share is about the community is the courses that we have done so far. So we started this quantum formalism community in 2020 during the COVID lockdown. So the first course that we did was something I called Foundation Module. In a nutshell, this is more or less like linear algebra. So we covered, vector spaces, complex vector spaces. In this case, we emphasize on. But before that, we we went, we started with sets, we went into, groups and so on. We built the layers until we got into Hilbert spaces, finite dimensional Hilbert spaces. So this is like CN, and then the next course was something on topology. Yeah. Okay. So Diego is saying it was great. Everyone should take. Well, the courses are available on our YouTube channel. So if you have patience, I know it's very boring to do to catch up with things, especially when there are like so many sessions, But at least for those of you who want to, who are maybe not coming from the background, don't have the prerequisite I was mentioning, maybe this could be a good starting point, especially on the linear algebra front. So you need to know what a vector space is, in particular a complex vector space. Yeah. And if you know finite dimensional Hilbert space, that's even better, because the transition, infinite dimensional Hilbert spaces are, completely different beasts anyway. But, knowing what a Hilbert space is definitely will help, Though we'll do some review. Carlos will mention that, and we'll have Max, who is an analyst, functional analyst, who will be doing whenever needed, in the study sessions, or through videos and these things to help people, depending on how people are struggling on the mathematical front. Yeah. So we did a course on topology and differential geometry. Why? Because after the foundation module, the target was we're going to do a course on Lie groups and representations. But Lie groups are not just algebraic structures, so we needed to do something on topology and differential geometry, because Lie groups are also smooth manifolds. So people need to know what smooth manifolds are, and then during the course, on Lie stuff, people will then know how the manifold structure and group structure are used. Yeah. So after that, we started with topology and differential geometry. This is also on the playlist. We did a course on group theory as well, a crash course, and it was some people found it funny as well, because we covered we went a bit sidetrack, not in the sense of covering stuff that are not necessarily to do with quantum, like cyclic groups, for instance, in a sense, in the context of cryptography, where we covered Diffie-Hellman, the application of cyclic groups to Diffie-Hellman, key exchange. So it was fun as well. So these are the completed courses. And then currently we have ongoing, the first one is functional analysis and measure theory. I definitely recommend you this. I think I already in the course announcement, I recommended people to review. I think it's lectures 10 to 15 or 11 to 15, something like that. Because you will learn what topological vector spaces are, and then you go towards the Hilbert spaces, in particular these spaces that you will encounter in Carlos's course, because infinite dimensional Hilbert spaces will show up there. Yeah, so I recommend you. The playlist is also there on the thing on our YouTube channel. The other course ongoing. There is only one lecture to go. The lecturer actually has moved from US to France. So he's a little bit busy with sorting out his normal, but he will be resuming on the last lecture. And then we will have a workshop on the application of category theory in machine learning. So, stay tuned with that, subscribe to our newsletters, to quantumformalism.com or to our Substack, you will get all these things updated for you. And then there's another course going on. This is a course on software verification with Lean. So this is also something you can enroll if you are interested in verification. This is now week 4. Lecture 4 has gone past. Yeah. So you can go to our GitHub repository. You will find all the links to the resources that you need to attend this. And the emphasis is on this software verification will be on functional programming. Verification of programs written in functional programming. So this is what we have right now going on. And the upcoming stuff is actually this quantum hardware. Carlos will go through this in his side of this Q&A. in particular with emphasis on this part of the course will be on optical models. Carlos will go through this with you. And at some point, we keep pushing this Lie groups and representations. This is something that we will probably have later this year, possibly early next year. It's just it has to come at the right time. And after that, we want to run a course on geometric quantum machine learning. So there is a lot of things on Lie groups and representation theory that will have applications in geometric quantum machine learning thing. So we'll have maybe 4 to 6 lectures, like a crash course on this to make it faster. So this is what we have right now upcoming. There are other stuff that we have planned in parallel, but we haven't gone to the stage where we can make any announcement. Okay. So before I hand over to Carlos, so why, if you look at our profile, we've been very vocal about, focusing on like quantum algorithm stuff, but quantum hardware really matters, So I would like to emphasize 3 things. The first one is on the algorithm design side. When you are designing an algorithm, it's very important to understand the underlying architecture of the quantum hardware that you're writing your algorithm for. It's very, very, very important, because this enables you to tailor the algorithm in order to take most out of the particular device that your algorithm is targeting. Those of you who know, we lived in this NISQ era where there are a lot of limitations. Not just the devices are have a very little number of qubits, but they're also very noisy. So you need to know how to deal with that. And there are a lot of other things that you can take into account. At the hardware level, your knowledge, because as I was saying before, the abstractions haven't been built, so you need to understand the hardware, in order to write better algorithms, targeting, whatever devices that you want. Scalability and resource management is another thing that's very important, right? Because of the limitations I was mentioning, in terms of, number of qubits, the gates available being implemented on your specific hardware. And other stuff as well. So you need to take all this into account, by having a good understanding of the hardware. It makes you basically a better quantum algorithms writer, that takes into account all these limitations that we have, So yeah, so this is one of the reasons that we decided to, from our end, that we should have a course on quantum hardware, in particular to a course series, not just one course. So we'll have a series of this course will be a series. So there will be different hardware architectures, models to implementing quantum computation that we will be covering. One of the starting point, as Carlos will mention to you in his side, will be focus on optical models. So yeah, so this is just a three key things. There are more things to why, as even if you are just interested in software and algorithms in the quantum computing realms, understanding the hardware is really very important. Okay, so I hope for those of you coming from a developers background, in particular those who are interested in pursuing a career in quantum algorithms, hopefully this will be very useful to understand the physical thing, the physical principles underlying these quantum hardware devices that you often, you use Qiskit or, Amazon Bracket or whatever to submit jobs to them. So you will understand, you will have a better understanding of the physics underlying it. I used to joke always, to say nature doesn't give a damn about Python. So it doesn't matter how beautiful your Python code is, if it cannot physically, if the physics underpinning the quantum hardware cannot implement your Python code, it's useless. So yeah, this is just a motivation to why you should, learn, have understanding of quantum hardware, and therefore the underpinning physics of the topic. Yeah, so a quick rundown. So we'll a high level one. There will be more details over the coming days that we'll provide with more resources. like the Lean channel and this, the Zulip channel. So the start date we have provisionally is on Friday, more or less around this time, 6 p.m. British summer time. And then the idea is to have, like a weekly sessions. This can change, and we want pretty much this thing to be dictated by the people actually who bother to show up on the live sessions. So the last thing we didn't want to do is to send a survey beforehand, and people who have no intention of taking part, for them to have an impact on the thing. So we'll let this roll based on people on the thing, those who are actually taking part in the live sessions, and then the case study session. The course study sessions. These will be agreed upon, the completion of each lecture, by the community members, to decide their availability when they want the course, the study session to take place. I think Carlos will have some constraints on which times of the day, of the week is available. So I'm pretty sure we can work out something around the times. Okay, what is the duration of the course? That's a very good question. Can we come back to that maybe after Carlos's thing, because it's more or less a little bit open-ended question. Yeah, we have some rough idea, but I'll let Carlos take on that. But I will also jump in after. Yeah, good question. Yeah, if I don't, because there's you pasted your question on the chat, just remind us later, or you can just post it on the Q&A. Thing, so it stays there. Yeah. Okay. So, and then there is a course certification. Yeah, we pretty much welcome the certification, but this time we really want people to submit a project. So this the course certification will be based on even though it's a course series, so it will be based on topics, each topic. So in this case, the starting point for the certification will be on the course on this module on optical models. So you will get a certification on on quantum hardware, but with the optical models, and it will be like a project submission. It can be a group or individual. If it's individual, we are probably looking at no more than 3 people, because when you have too many people, it's hard to see how many who contributed more. It's a little bit more kind of in terms of collaboration and contribution, evenly more than or maybe 2 people. Yeah, but we'll leave it 3 people just in case, to make it more flexible. Yeah, no more than that. That's what we are thinking. And then we'll people can choose whatever topic they want within this thing. Maybe people will get inspired during the sessions, and maybe Carlos can come up with some suggestions during near the end of the course to see those who don't have any idea on where to what project, what to tackle, and these things. I'm pretty sure you will get inspired during the course, because this is an emerging thing. There's a lot of problems. There are a lot of interesting stuff that you can do. And one thing I forgot to add here, we will try to invite actual companies who work in quantum hardware companies that are actually implementing real quantum hardware to come and give a talk during, every once in a while during the duration of the course. So yeah, so we really hope to make it a very interesting course where you are not just learning boring stuff, but it's also like, something very, very interesting for you, exciting as well. And above all, you build your network within your classmates and ourselves and so on. Okay. And the specific repository for this course is not available yet. We will put it up, but in the meantime, you can follow us on this. There's actually a Quantum Formalism LinkedIn page as well. Please feel free to follow us and follow our GitHub repo. This is where the resources will be available and so on. So I will stop sharing, and then I will hand over to Carlos, and then maybe wait until the end so we can take the Q&A together. Any questions that you have. So Carlos, I will stop sharing, and the floor is all yours. If you want to share anything on the screen, or you want to just talk over it, it's up to you.
Yeah. First of all, I would like to thank Bamborde for giving me this opportunity to have this course. I hope everyone can enjoy. And thank everyone. I mean, 20, I think 17 people, 21 registered, 17 is here. So
Yeah.
Good to know that, that so many people are interested. So a little bit my background. I mean, I'm a physicist. I mean, I finished my PhD in 2009, and I was working with a completely different thing, like working like things related to quantum physics, but related to like cosmology or black hole physics. So a mix of quantum physics and general relativity. And then I did some postdocs during all this time. I mean, but it was during the pandemic that I was like start like reading something and get interested in quantum computing. So I decided like learn something, and I started like I think most of the people that is coming in the area, like starting like seeing in the IBM things, in Qiskit, these things. But because I'm physicist, I'm not like a programmer, really programmer. I know how to use Python, but basically not a developer. And I was thinking, oh, how this works in real life, in real world. And so I decided to study a little bit about the hardware things, how quantum hardware works. And I think I met Bumblebee, I think in April this year, something like that. And he told me about the company, the Zaiku group, and the course that he was interested. And then I suggested him, oh, maybe a course about quantum hardware. I mean, I'm not really specialist because my PhD was not in this thing, but I mean, I know the basics, some basics behind, and I'm really interested in this and how people say that the best way to learn something new is teaching. So this is one of the reason. I mean, we are learning together. I mean, I have the things prepared, but we are learning together this quantum hardware things. So I have some slides to show you that give a broad idea about the course structure. So let's see how to share. I'll share my screen. Let's see how.
Yeah, just started loading. Yeah.
Yeah. Okay. Can you guys see this?
Yeah, I can see. Can everyone see?
Hello?
Yeah, I think everyone can see. Yeah.
Oh,
yeah.
Okay. So the idea is give the physical principles for quantum hardware models. I mean, as Bumblebee told me, said to you guys, the idea is have a series of course related to quantum hardware models for quantum computing. This was the first part, let's say, like that, and it's about quantum optics. So this is me. I mean, Carlos Bessa. I'm from Brazil, and as I told you, I finished PhD in 2009. And Max Arnold, he will help me with some things during the course. He's a mathematician, by the way, and he works for the quantum formalism Zaiku group as well. So this is the first part of a series of course we are thinking about. It will be like quantum optics will be our main topic. I mean, our main model, quantum hardware model to do computation. So, and I decided to start with quantum optics because in the past I worked a little bit with quantum optics with different applications, not quantum computing applications, but I work a little bit about this with this topic. So, I mean, to me, it would be simple to start with quantum optics models, but we are planning to see other models in the future. I mean, ion trap, superconductivity. I'll talk you. I'll show you guys. So this is the idea for the, I mean, for the all the parts from the quantum models that we want to cover. So in the first part, this will be the part like harmonic oscillator quantum computer, and these two optical models like optical photon quantum computer and optical cavity quantum electrodynamics. Okay, so in this first one, I mean, it's not a real thing that you can do in real device, the harmonic oscillator. But the thing is, the theory we learned behind this topic here will be very helpful in the other models. So this is what I'm planning to show you guys in this first part of the course, and I think like 20 or 24. I've answered one question here in the chat. I think about 20, 24 lectures, something like that, will be enough to cover this first part, because I think I also need to show make some reviews about quantum mechanics and also quantum optics. So I think before we start really discussing that, we should like discuss something about basic quantum mechanics and quantum optics too. At least the things that will be necessary here in this first part of the course. And once we have this, I mean, we can see with more details like the models, like the hardware models, the quantum hardware models. So as Bumblebee said, this is the idea is to have a series of courses. This would be the first, I think, until December. If it's 20 lectures or 24 lectures, something like that, probably once per week. So probably in December we finish this first part. So in the next year, we may be planning to have the second part, like we'll discuss ion traps. And I don't need to make the same reviews about quantum mechanics, because we had discussing these reviews here in the first part. And then we follow. I mean, this would be like the third part, superconductivity models, the fourth part, and so on. We see. But these last three is for the next year probably. Now we will focus only in the quantum optic models, and especially we are treating about these three models here. I mean, all you need quantum optics, but a little bit different. These two here are not exactly the same. We need some basics about quantum electrodynamics that we will cover here in the course also. And yeah, so the idea is to have this. So this is the main idea in the course, and I'm planning to give you guys like some homeworks, and if you guys have like some doubts to solve the homeworks, we could like make some extra sections. Me or Max, that is the other guy, we can help you guys, I mean, with the homework part. And about the project, yeah, we as Bumblebee said, we are thinking about what could be a project. But one thing I have in mind is, because during this course we will see like how in a real hardware model, how you can do, let's say, some gates, like a CNOT gate. We know how to implement this in Python using, the different libraries we have, but how this would work in a quantum hardware, using optical models, how a CNOT gate could appear, the logic of a CNOT gate. So we'll see this during the course, a CNOT gate, X gate, and so on. So the idea, maybe for one project, is you guys thinking like in a simple like algorithm that you could implement very simple, let's say in Python, but say is like how you do this, how the real device would do this, how these gates you are putting in your Qiskit codes or other codes, but how you could how this would work in the real quantum computing, based in the things we will learn like during the course. So how would be the hardware? So you have the program, the algorithm, or the code in Python, and how would the hardware part, the theory of the hardware part would work. This is one thing. So we will see some examples during the course, like as I told you guys, like a CNOT gate, and how we implement this in a real hardware. So yeah, I can see if you guys have other questions. Let's say, I don't know. I think I answer one of these questions. Yeah, if you guys have, yes, quantum hardware models, as George is. Yeah, we're using the models we are using is like based in quantum optics. We're using these models. At least in principle, we're using this. The other thing is, I would say in the end when I show the references, but I'm planning to show this, and in the end of the course, maybe we see like a more, because this is like an introduction, right? An introduction part. So in the end of the course, maybe we see more, let's say, advanced topics. Advanced topics related to quantum optics, more, let's say, modern topics. Let's see the questions.
I think about just this thing with the. So go ahead, Carlos.
Yeah. So okay. So this the presentation. Okay, so the reference are using is this book here, Quantum Computation and Quantum Information. I will follow this book. It's this one. This, I think, is the second edition. And as I said, this edition is the second, and I think they don't have the third edition. So this edition is from 2010. So we have about like 10 years. What we see here is things like 10 years in the past. From 2010 from now. So in the end of the course, I'm planning like to show something that is not covered by the book. Something more that people are using nowadays, because you guys know this is the advancing. This topic is changing and it's advancing every day. So yeah, so we use this book is the reference, and as I told you, because I think people have different backgrounds, and in principle, to see these things here, we should like some prerequisite. You should know a little bit about quantum mechanics and also quantum optics would be important. So some reference about quantum mechanics, I mean, there is several of books about quantum mechanics. This is the two I'm suggesting here, the two classic books like quantum mechanics, this volume 1 and 2 coin. I will use something to review quantum mechanics from this book. And the other is this Sakurai book, is also classic, very all physics students studied for these two books in the past. So, but I mean, if you guys have different books, you probably has the subjects necessary, I mean, to follow the course. Don't need to be these two. This is just some suggestions. And also quantum optics is important. So the books I'm suggesting is this one, Scully and Zubari. Is good. So I use some things from this book, and the other is this other classic book, The Quantum Theory of Light, in London. So this we use something. I will use something from these books to make some review that will be necessary during the course. So yeah, so let's show here. I have some PDF from the Nielsen Schwing book. I think it's better I show. You can see that I changed the.
Yeah, we can see.
Yeah, so.
Or at least I can see it.
Yeah, this is this book, okay, the PDF. So you can see that they make a review, the book make a review about quantum mechanics. So I will use something that is in this book, but I'll take some that like the Sakurai book and the Coin Energy book, the books I suggested to make the review. And what I'm planning to cover is this, chapter 7 of the Nielsen Schwing book, and we try to cover like this to here. So from section 7.1, the introduction, until the section 7.5. Okay, so it's the different models. The three models that I put in the other slide is this one: section 7.3, 7.4, 7.5, and 7.1 and 7.2 is basically some introduction. I mean, things that it's important that we also talk about. So that's why I think this course will be the longest from the others. I mean, this first part, I think we will be able to cover this until December. I hope so. And then the other parts will be these ion traps, nuclear magnetic resonance, and the conductivity that this book did not cover. I mean, it did not cover well. I mean, just make some comments. But it's important. I mean, next year we probably will see about this superconductivity topic. So, but now for the course, the part 1 of the course, I'll try to cover until this chapter 7 from Nielsen Schwing book, and finish in section 7.5. Okay, starting 7.1 to 7.5, and make some reviews about quantum mechanics in quantum optics. That will be at least the part will be necessary here. During the course, if you guys say, "Oh, don't need," I mean, we can follow. Don't need so many reviews. So okay, we can go faster. And then in the end, yes, in the end, let's say if in November we finish this, we covered here. So as I told you before, because the book was written in 2010, so we have a gap like 13 years in this field, like quantum computation, that is increasing a lot. So I intend, like in the last, let's say, 3-4 lectures, to see more modern things. And you guys even can suggest, oh, I have this review paper here about quantum optical models that was written, let's say, 2016. So we could like talk a little bit about in the end of the course about this. It's okay. I mean, we can try to do. I'll try to do my best to do this. So,
and I will just say,
yeah,
go ahead.
Like,
Sorry.
to see something more, let's say, modern. Not that it's not modern, but this is like the introduction that we need to do to work with quantum hardware today, and especially in quantum optics. Like, this is something like an introduction. This was like modern in 2010, but since 2010, like some things, new things.
This is one of the reasons that in the course I will try. Sorry, Carlos. One of the reasons I will try to invite people actually building hardware with these, with whatever the particular hardware architecture that we are covering. In this case, people building with the optical models. So you will see in these talks actually how they go. Hopefully they will expose enough through a webinar series about with the different companies, how they take different approaches to implementing these things. And I think this is also related to Hugo Christian's question here. We are going to see how to design hardware with some software. Well, this is something that definitely we would like to see, especially with these guest talks that we will be inviting. So I'm not sure if by default this course will be touching that. Because this is just to start with. This is an introductory course, but maybe we can. After we go through all the models that we want to cover, there will be a follow-up series where we can emphasize more on this aspect of this thing that you are asking. There is another question also. Sorry, Carlos. I know I disrupted your flow, but
no,
there was
no
another
problem.
question. How is duration? I think, as Carlos said, we hope to maybe by December. I guess this is because it's open-ended. This is why I was saying at the start. We hope maybe by December most of it is covered. If not, maybe we have to extend it. And another thing is maybe this is a flexibility we have to. Carlos will possibly have. There might be some period of time from the start of the course to December where maybe there could be a double lecture per week, something like that. So this is also a possibility. This will be something that will be discussed with the class to see how fast they want to finish it. But I want to emphasize one thing: we are not optimizing for speed. What's more important for us is that people are learning. So it's not so much. Okay, I've completed this, and this thing is. This is one of the reasons because we want people to submit coursework as part of the certification. So we will be, as long as it takes to cover the stuff, even though we are targeting to maybe end of December or something. If necessary to extend it by 1 or 2 months, it's so be it. From our point of view, the most important is to have enough people to have enough time to give them the chance to actually understanding this thing and then going on to doing something useful with the knowledge they acquire. Yeah. So there's also another question, Carlos, is to understand quantum hardware. Is it necessary or useful to understand the classical computing hardware? This is a very tricky question. I would say no, but it's good to know. I guess this is more of a related to the question, I guess, deeper question about, to understand quantum mechanics, do we need to understand classical mechanics? Because the two things are completely different. We happen to learn classical mechanics first, but quantum mechanics is more fundamental. So in a sense, you could discard, you could have discarded classical mechanics and start with the quantum. So that way, you won't be confused, because it becomes first nature. All the what is considered weird behavior of quantum world wouldn't be weird because you started with it. The reason why these things are weird because we start to learn classical mechanics first. Yeah. So in the case of computer, I think you don't necessarily, but it helps, because at the end of the day, especially in these first few decades, until we have a fourth-order quantum computer, and even after, there will be some sort of integration between quantum hardware and classical hardware. So it is helpful to understand, and I think I believe most of you are coming from computer science background, so this is already something that most of you already will have. So but it's a complete paradigm of computation. So in theory, if you never have been exposed to any theory of computation, in theory you could be exposed to quantum computation without obviously in practice it helps, because the computers, the control system, all these stuff that are controlling at the moment the quantum hardware stuff, these are all classical machines, so it definitely helps to understand. But theory-wise, you don't in anything. It's not really necessary, I would say.
It's not a prerequisite. No?
Yeah. So sorry for that. So Carlos, you were sharing.
Yeah. I mean, it's not a prerequisite about this. Yeah. We can follow, like, even if you don't know details about classical hardware, but if you know a little bit, it's better, but I mean, it's not really necessary. Okay. So, more questions? Okay, Fernando, welcome. I hope, as Bumblebee said, like, I hope we can finish. But if you guys need, I didn't say about the lectures, the structure in the lectures. I mean, I'm planning like to show during the lectures, show like some slides, but when we need to do calculations, and we always need to do calculation, I need to use like a digital table, I mean, in a online whiteboard, because I think it's better. I mean, sometimes we have like long calculations and show calculations in slides. It gets boring, so it's better we do live. And I also like intend like to at least the main lectures. I prefer like make like live with you guys, because if you guys have questions, and then I can try to answer like when I'm doing the calculations, and I can stop and okay, and answer the question. So during the lectures I will show some slides and do the calculations in my digital table, because I think it's better. It's better this way, and I'll try to to show. We cannot show all calculations, because if you see like the Nielsen Schwenk book, that's here some example here. You see, he is very, like, let's say, dense book. because it covers a lot of subjects, but he sometimes is not so clear in the calculation. Let's say something like here. I take some. Starting here, okay. So the course will start here with things, and let's say this box prop. This is like a very traditional problem that all physicists students see in the undergrad, and this is, I mean, he show like the solution here in 3 lines, but usually this is a long calculation. So I'll try like to make with more details the calculation during the course. Of course, cannot show everything, otherwise the course will be too long. But I mean, most of the time when possible, I'll show more details in the calculations than the book. Because as I told you, this is dense. One page has a lot of subjects, and we try like to understand better, I mean, each of the main steps. And the book has the structure of the book, which I like. Also, it has a lot of, let's say, exercise, and some of this exercise I will give you guys to like here. Some of exercise I'll make during the classes, but some others I'll let you guys like homework and to practice something. I don't know if most of the people is from physics. I don't think so. But people from computer science, engineer, will be very, very good if you guys could like make some of this exercise. Some of them I'll make during the sections. But I cannot make everything. Okay, go ahead, Mohammed.
Yeah, no, your slide, the one. Can you go back? This is very interesting, actually. the one with the commutator there. Yeah, this is like totality. You can see a physicist that where the momentum, the xp, the commutator xp equals I h bar. So behind it there is a there should be an identity there, but physicists omit this.
Yeah, I'll try like. Yeah, I'll try like to make the.
But, it should be an operator on the thing on the right hand side. But so you can see this is a hint of this thing being written by a physicist. Yeah. But Carlos will be more rigorous with this.
Yeah, I'll try to be more rigorous. I mean, Max will help me. Yeah, identity operator should be there. Yeah, because X and P are operators.
Okay, so any more question or anybody? I'll actually open the stage if somebody wants to make any comment. It doesn't have to be any question to do with the course, but any feel of why, for example, they want to take a course on quantum hardware and these things. I'll give you an opportunity, like to come on stage if you want. If not, maybe we can end it here, and I will be following up with the resources. Yeah, someone is jumping in, so welcome, or maybe not.
Oh no, I stopped sharing.
Oh, okay. Any brave person wants to come in and make a comment or something?
Questions?
Yeah. Okay, I'm pretty sure in live sessions people will because we really want this thing to to be interactive and be discussion driven as well. Because this is how you learn and you get into other people's line of thoughts. So yeah. Okay, so in that case, maybe we can end here if nobody wants to come and jump in. One thing I want to just comment about the platform the online tend to use for the live lectures. I mean, in principle, I'm happy if we could use this maybe to start with, but if it's becoming a little bit complicated to, not smooth experience because of the time. Maybe we can move to Google Meet. The lectures will still be recorded, of course, but yeah. For communication is the problem with Discord we have is not LaTeX friendly. That's one of the reasons, to type a LaTeX thing is not as straightforward. That's one of the reasons. We are trying to migrate to Zulip for this, because then it's you can it's already LaTeX is natively integrated with it. It's much easier to when you are writing your thoughts, writing a mathematical thing, it's straightforward. I find Discord very very ugly and natural in terms of the support for LaTeX, which makes it hard to have a mathematical discussion on Discord. Are we going to use platforms such as Canvas for the course? Canvas is this teaching thing, right? I don't think so. So the recording, so we will the tools that we will use for the recordings is either Google or this thing, this Crowdcast. For the repository stuff where the lectures will be, we'll use GitHub. For storing the lectures like recordings, we'll use YouTube. And for chat, we will use Zulip. But we are actually planning, this is probably not, we have to wait until probably next year. I realize maybe we are getting to a point where we need a learning management system. So we are working on something on plan to create a learning management system for quantum formalism. So everything is in one place. So this is something that we are looking at doing, but unfortunately it won't be done as before the start of this course. So it will probably be done at some point next year, because we still to decide whether we build something from scratch or use some open source stuff like edX. Some people already suggested that, but yeah. So for the time being, it's all like all over for there will be like different places where you have to go to get the resources. Yeah. Oh yeah. So the first lecture will be on September 1st. Yeah. Unless something it's provisionally scheduled for September 3rd. I will be sending the updates for all of you guys. With the links and resources, the Zulip channel and so on, so you guys can join ahead of time. And maybe Carlos can write up some resource, some of the references that he mentioned. We'll write that and put it on the thing on the GitHub repository for the course for people to go and use before as a prep.
Fernando is asking if the book is available online. We have to buy it. I mean,
it is available. If we have a copy. I have a copy. If you email me, if you reply to them, we'll probably share it on Zulip. Maybe we can share it on private. Yeah, it is available. I mean, if you are if you have enough patience, you can yourself Google it. You'll find a link somewhere with it.
Yeah.
I'm sorry, Miss Nielsen and Chang. I'm sure it doesn't make that difference.
I mean, I have the physical book, but I also have the.
He makes money with the physical books, so.
I have this one I find in internet, the PDF file. I mean, I can share.
There's another comment by our friend George. George, how are you? My problem has been that the physics looks like math, but the problem need to be translated to math before I can solve them. So I guess this is a question to do with the cultural differences between a mathematician and a physicist, right? Yeah. So physicists tend to focus more on getting it right on the computational aspect of things as opposed to like on the rigor thing. Actually, there's a nice video I will share on YouTube. I think Richard Feynman explaining the difference between a mathematician and a physicist. You should probably watch it. Let's see if I can find it now that we are talking about it. Those who want to drop out, they can drop now. Difference between physicist and mathematician, Feynman, something like that. Very hilarious. So if you are coming from a mathematician, from a mathematics background, very often physics books are a pain a little bit.
Messy.
But yeah, this is a video. I'll share this. on the chat, so you can watch it on your own time. But it's very funny. Yeah, people coming from a mathematics background normally struggle with the thing. Yeah, so he's saying the example you gave of the commutator. Yes. It's is a thing. Yeah, that's the thing with the physics, the cultural differences, and in quantum mechanics in particular, because it's a very very interesting topic, and I won't say like very. I lost the word, I would say, but on this thing of rigor stuff, like on the foundational stuff, there is this very interesting code that used to. I don't think it was Feynman. It was someone else to say, shut up and calculate. The foundations stuff of this, of the topic. What it all means, the interpretation, and all this stuff. Yeah, but physicists traditionally have been mostly into doing calculations and these things, and very often actually they get the right results, but then mathematicians have to come in and formulate the stuff in a rigorous fashion. One example is Feynman path integral. That the original formulation of it's nothing to do with integrate, it was a horror for mathematicians. But then years later, people, I think it's now called CAC mode or something, CAC something. The formal version, the rigorous version of it. But what matters, at the end of the day, physicists are there to actually explain nature. So if they can write, they can get to the right calculations. So be it. That's the way physicists think. Yeah. And say, yeah, you gave the example of the commutator. Yes. And the notation also, sometimes it's a little bit, a mathematician would probably use some other notation and some terms. For example, one thing you will see, I hope Max will emphasize this difference between what's a Hermitian operator and a self-adjoint operator, this subtle stuff. In finite dimensional Hilbert spaces, the two things notions are equivalent. But when we are considering infinite dimensional Hilbert spaces, there is some subtle differences there that you have to take into account, this is something that Max, the analyst, will go through with you on his review on Hilbert spaces stuff. Yeah. So anyway, this is already a sidetrack with what we were set out to do today. So if nobody else wants to say anything or have any questions, maybe we leave it here. And I certainly look forward to seeing how the course goes, and I'm looking forward to actually myself learning. I'm coming from a mathematics background, so I still need to learn a lot of physics. So yeah, I'll be whenever I can, I will be attending Carlos's lectures as well.
Yeah, and then I hope I can learn some mathematical rigor too during this.
Well, we will be. I think Max will be pinning you.
Max will help me.
You need to say this. Yeah, we are trying to do this because at the end of the day, the name of the community is quantum formalism. So we need to emphasize try to be as rigorous as possible, but not lose your the physics side of things. So this is not a. It's not a pure maths course. It's a physics driven course, but at the same time, yeah, we need to be as rigorous as possible. Yeah. Okay. Well, a lot of people are saying thank you. I guess. Yeah. Like Joe, the rigor without rigor. Yeah. Well, thank you, Hugo. We hope to see you in the course as well. Thank you, Mohammed. Thank you, everyone. Ajay, Annie. Everyone on the thing, and we look forward to having you. I'll be following up with everybody, so basically everyone who signed up for the course will be, you will have access to it. Now, whether you will, stay along with the course, that's something else, because the level of difficulty, especially on the mathematical side, things will become harder. But if you dedicate yourself, you do the reviews, you follow the structure, I'm pretty sure you will be fine, during the course, and you will get the certificate, So that's exactly what we want, So yeah. So Carlos, you want to make any final comment before we go?
No, just like to thank everyone that was here, and I hope we can play and have fun together in learning these things, because in some sense it's new, a little bit new to me also. I mean, but I mean, we will learn together during the rest of the year, and learn some math, learn some computation, and try to learn some to teach some quantum physics, quantum optics for you guys, and apply to these things for quantum computing, which is a very interesting topic, current topic from life science. Let's say like that. The things happen every day. Every day has a new thing. So let's see. I think it would be good. It would be a nice course, and we have fun together. And thanks a lot, everyone, that George, Diego, and the other guy, Mohammed Reza, and Hugo, everyone, Fernando, everyone. So thanks. And thank you, Bumble Day, for this experience.
Yeah. So yeah, thank you again, Carlos, for making your time available. And yeah, I'm sure everyone, we are all excited. So yeah, everyone, we see you. Just this thing will be recorded, will be uploaded on YouTube again later if you want to review anything. And it's also a way of you finding out the playlist for the course. So I'll follow up with all this, and next week with Zulip, with the GitHub repository for the course and so on, with some references, so you can do some prep work ahead of time to make it easy for you. So yeah, so in that case, goodbye everyone, and have a good weekend. I see you all. I hope to see you all on the 1st of September. Okay, bye.
Okay,
Bye.
bye. Yeah. Bye.